Today we're going to continue our examination of motion by looking at graphs of velocity when the velocity is not constant. In previous examples, the velocity was always constant. The graph of constant velocity against time is a horizontal line. When the velocity changes, it can be increasing or decreasing. Now let us take another example of a car at traffic lights. The car is still till the lights turn green, then it starts to accelerate. Increasing its speed till it reaches its cruising velocity, which it maintains till it sees that the next traffic lights are turning red. So the driver slows down till she stops at the new lights. The slowing down is called deceleration, but we can also say it is negative acceleration. From the graph of the car's velocity over time, what is the acceleration? Well, the acceleration is the slope of the velocity time graph. We can see that in section A, speeding up from the lights, the final velocity is 60 kilometers per hour, and the initial velocity is 0. So the change in velocity is delta v, which equals v final minus v initial, which equals 60 minus 0, or 60 kilometers per hour. The time interval to gain this speed is 4 seconds. So the change in time equals delta t equals 4 minus 0 equals 4 seconds. Putting these numbers into our equation, acceleration equals a equals delta v divided by delta t equals 60 kilometers per hour divided by 4 seconds, and this equals 15 kilometers per hour per second. In section B, delta v equals 60 minus 60 equals 0. Therefore, the acceleration equals 0, divided by delta t, which is still 0. We do not need to know the time interval. If the velocity does not change, the acceleration is always 0. And in section C, the car slows down again. Delta v equals final v minus initial v. So this is 0 minus 60 kilometers per hour, which gives us a negative 60 kilometers per hour. This negative is very important. Delta t is positive. Delta t equals 20 minus 16 equals positive 4 seconds. The acceleration, therefore, is delta v over delta t, which is minus 60 kilometers per hour divided by 4 seconds, or minus 15 kilometers per hour per second. The negative sign means we have deceleration. Every second the car is traveling 15 kilometers per hour slower. While we have this graph, let's practice by calculating the displacement. This is the distance between two sets of traffic lights. How do we calculate displacement from a velocity time graph? From the area under the graph. Remember, on a velocity graph, the slope of the line is the acceleration. The area under the graph is the displacement. If we look at the graph, we can see that it is made up of two small triangles and one large rectangle. The area of a triangle is half its base times its height. In this case, the base is the time interval delta t, which is 4 seconds, and the height is delta v, which is 60 kilometers per hour. But how can we multiply seconds and hours? Well, we can't, so we have to convert the units. I'm sure the distance between traffic lights can be measured in meters better than kilometers. So I will divide 60 kilometers per hour by 3.6 to obtain 16.7 meters per second. If you can't remember how to convert units, go back and view the units tutorial. So now we can find the area of the first triangle. We multiply half of the base by the height. So we have half times 4 seconds times 16.7 meters per second. Notice how the seconds cancel, and we are left with 33.3 meters. This means the car traveled 33.3 meters to reach its top speed of 60 kilometers per hour.